Right, welcome everyone. It's a pleasure to have Gillat Cole giving a lecture on complexity theory at the summer school. Gillat is a faculty at Princeton University. He got a PhD from Weizmann Institute. He's a recipient of the NSF Career Award, the Sloan Fellowship, and Gillat has done some phenomenal work on understanding communication complexity, information complexity, and also particularly the relationship between the two. And she's going to tell us about some of the great ideas in complexity theory. Please.
Oh, thank you. So I'm very happy to be here. Thank you for coming. I'm going to talk about theory of computing, and this is kind of my area, complexity and theory of computing, and I think it's a really, really cool area for several reasons. One of them is that from our point of view, computation kind of underlines everything that happens, or computational limitation drives everything that happens. And I'll try to explain probably tomorrow that you can view computational limitation as a force of nature, like gravity. Some things happen for computational reasons, like some things like an apple will drop because of gravity. And another thing I really like about theory of computation is that it allows us to address very philosophical issues in a mathematical or rigorous way. And this is kind of what I'm going to talk about today. I know that some of what I'm talking about is covered in some undergrad programs, not all, so you may be familiar with this, but I'll try to take a more kind of high level and philosophical approach and not obsess about details, but tell you kind of the processes that led us to those results. Okay, so that's kind of weird. I don't see anyone. Let me see at least some people. Okay, good. So hi. Okay, the first thing I want to touch upon is computability theory and the question of what can be computed. And by the way, please feel free to just unmute yourself and ask questions. I'll be very happy to take questions. Okay, so maybe anything can be computed. This will be awesome. Of course, I need to tell you what I mean by anything, and I need to tell you what I mean by computed. So here is my definition of anything. Anything is all functions, let's say Boolean functions. For me, and can you see my cursor where I point to? Yeah, you can. Okay, great. So let's just, for the sake of this talk, think about function from the natural numbers 1, 2, 3, or 0, 1, 2, 3 to 0, 1. So those are Boolean functions. And don't worry about this too much. If you want to, if the function takes a string, the string can be mapped into a natural number. And if the output is not just Boolean, then you can kind of massage this. You'll see it in the homework. So let's not worry about this. Let's just think of functions. And so I want to compute functions. What does it mean to compute a function? I'm saying that to compute a function is to write a Java program that I give it the input x, a natural number. It will give me f of x, a 0 or a 1 correctly. I'm not saying it needs to be efficient or anything. It just needs to, terminate in finite time. It needs to halt. And I want to ask, what functions can be computed, whether everything can be computed. And when I say this, usually the first question is like, why Java? I don't know, but basically I think this is what people know now. But any programming language is completely fine. Any reasonable model, by reasonable I mean a model with finite description, like a Java program is like a finite object. It's what's written in your file. So anything like this is good. Actually, my favorite programming language is Turing machines. Probably the only programming language for which you won't get a high-paying job in the tech industry. So this is why I work for Princeton, and it's extremely painful to write in Turing machines, but it has its pluses. Okay, so personal preferences. But anyway, the reason we were not obsessed with like what exactly is your computational model is this Turing thesis that says that the notion of algorithms is universal. So everything that can be computed on any physical computer, on any like thing that you can produce, can be computed using a Java program that runs on a regular computer. And okay, or can be computed by Turing machine or by a Python program and so on. Those things are equivalent. And I just want to note that this the Church-Turing thesis is a belief. It's not a conjecture. It's not a theorem. We don't know how to prove this, and we will never be able to prove this. The only thing that can happen is that we can falsify this. So, maybe some Martians will come and will show us their super cool computer that is using post-quantum something, something, and this will be able to compute things that maybe we can't compute. Okay, so it's a falsifiable belief, and I put this one here. It's kind of out of context, sorry, because this is the idea that scientific theory needs to be falsifiable is by Popper. And again, you want to construct something that, if it's false, maybe we'll be able to falsify it, and there will be a way to do this. And Popper is gave an example that back in the days, the European only saw white swans. So there's like a theory that all swans are white, but once you go out of Europe, there are black swans. So you can falsify this theory. At least there is a way to falsify. And some theories you can't falsify. You will never find a bug in there. There's no way to falsify them, and we think of them as less scientific. Anyway, this is a Church-Turing thesis. It's been standing for a very long time. We don't know of any counterexample. So for example, now we have quantum computers, but quantum computers cannot compute more things than a regular computer. We'll talk about whether they can do it faster, but if you don't care about running time, they won't give you more. But maybe Martians. What's happening? Okay, so this is definition. F is decidable if there's a Java program that computes it, or let's say computable, decidable, doesn't matter for our purposes. And if there's no Java program that computes it, it's undecidable. Okay, and again, I want to go back to my question. Can anything be computed? And I kind of hinted to the to the answer. Okay, so in our languages, the question is, is any function decidable? And this is unfortunately a hard no. It's a very sad result that is kind of easy to prove. And here is the one-line proof. There are just more functions than programs. Okay, so every Java program can only compute one function. Maybe there are many functions that are computable, by the no, many programs that compute the same functions. But you see, if you have more functions than programs, then no way that everything is computable or everything is decidable. So this is very sad. And if you haven't seen this before, then you may be kind of disturbed by the saying that there are more functions than Java programs, because both sets are infinite. We have infinitely many functions, infinitely many programs. What do I mean by this? What I mean is that some infinities are just larger than other infinities. There are sizes of infinities. We call those sizes cardinalities. And kind of the smallest cardinality of infinity is our countable sets. Countable sets are like the natural numbers. You can enumerate them. This is the first one. This is the second element. This is the third element. For example, all strings, the set of all strings, let's say binary strings, or strings over the English alphabet. This is a countable set. It's infinite, but it's countable because you look at the string as a word and you think about the dictionary order, the alphabetical order of this. This will give you an ordering. And some things are not. Some infinite set are not countable. For example, the real numbers. Think about the numbers maybe between 0 and 1, but all the real numbers between 0 and 1, you can't order them. You can't say this is the first, this is the second. They're so close together in a sense. And you can actually formalize this. You'll see it in the problem set. But what I'm saying is the set of Java programs is countable. You can order them. As I said, it's basically a string. Think of this as a string over the English alphabet, and think about the dictionary order. You can order this. It's a small infinity versus the set of function that is a larger infinity has a larger cardinality, strictly larger cardinality, and therefore there are just not enough programs for all functions. And this is a very sad result. And I think if you haven't seen it before, it's kind of striking. Not everything can be computed. Again, not about efficiency, just compute it. Just write some program that will eventually give me the right result. And we can do it for any function. Okay. So, okay, we have to kind of live with this. Not only that there are functions that are not computable or undecidable, almost all of them are undecidable, right? There are many, many more functions than programs. So most of the things cannot be decided. And I want to note that the proof I gave you, this one-line proof, is kind of a non-constructive proof. It's like a counting argument, an infinite counting argument. It doesn't tell us what function cannot be computed. And if you took any class in programming, you probably computed functions. Kind of everything you wanted to compute was you were able to compute. It may have taken you time to figure out how, but you were able to compute. Oh, I see a question. Okay, talk to me.
Hi, so I'm a bit confused about the previous slides that not all functions are computable. So for here, the definition of a function is that's like, I believe it shouldn't be the definition as a mathematical function. Is that kind of like a problem we want to solve so that we may not be able to use the computer to get a result of it?
So I'm saying what your problem, what you want to solve is this. You want to evaluate I'm giving you X, you want to give me f of X. I'm giving you the function. I'm giving you, there's a function you want to give me, but the function is from N, right? It's like an infinite object. You want to give me the answer for every X. This is the game. And I'm saying you won't be able to program this. I can give you a rule. I can define this function. Maybe the question is, how do you define the function? Right, but I'll show you a function. You can define the function, but I can't give you a program that will output f of X. Let me actually give you this. Okay, let's talk in like one slide. Here's a function, okay? So, okay, at the end of the slide, if you still don't understand what I'm hinting at, then ask me again, okay? It's a good question.
Yeah, sure.
So what I was trying to say is like, what? Okay, let's be concrete, right? Maybe everything you wanted to compute, you were able to compute, right? Someone gave you a programming assignment, you were able to compute it, to complete it, or if you didn't, then because you're not a good programmer, not because it's impossible. So what maybe everything you want is computable. Maybe it's only like stupid, crazy things that are not computable. So let me give you a very concrete problem that we really want to solve and we can't. And this is a program that this problem is called, or this problem is bug finding. I give you a computer program. Does it have a bug? Or let me be even more specific. I want to solve this halting problem. What is the halting problem? Someone gives you as input a Java program, just a file, just a, for just the code for the Java program and some input. I think that maybe this Java program takes one input. And we want to know if P halts on X. Okay, maybe it loops forever. Maybe there is a bug. Checks for a very specific kind of bugs. Are there infinite loops? Okay, so I just want to know if when I run your program, like a Java function, a Java program that takes an input X, if I run it on X, will it halt? I'm saying this is a function. Okay. Can you do it or not? So what is the function here? The function is the input is X, is P, is the program, is the code for the program, and is X. It's the input has two parts, the program and the input. And the output is 1 if the program, vice versa. So it's a Boolean function. This is all I'm computing. Okay, and it's kind of well-defined function. Okay, so an example of a function. It's more complicated than the sum or the product function, right? But it's a function. It has like, okay, yeah, okay, good. So yeah, we need to be concrete. It's a weird function, but definitely we want to compute this function, right? We want to know if you have infinite loops. Good. And as I said, it has application, obviously, to program verification. And, I'm a pure mathematician. So, what do I care if all the programs are buggy? Let me tell you why I really care about this thing. Here is a Java program, and now you can see that I can program in Java. Or let's assume that this is my Java program. It's a pseudocode. It's a small program. Let's read. For n equals 2 to infinity, it's an infinite loop. If 2n is not a sum of 2 primes, then halt. This is the program. Okay, if you want to kind of have Java program, I think this middle line needs to be another loop or two, where you go over all pairs of numbers and you take the squares, right? You check if they're prime, you take their squares, you sum them, and you see if it's 2n. But this is you can write it in a few lines in Java. It's a small Java program, and I really, really want to know if it halts, because can anyone tell me? Let me tell you. So if it does halt, is probably the oldest standing number theory conjecture. I think it's about 300-year-old. And it's a very simple conjecture. It says that every even number greater than 2 is a sum of 2 primes. And we don't know. This is a strong conjecture. We don't know. We don't know how to prove this. We did check it for very big numbers. But see, if this halts, then it found a counterexample. It found a number of the form 2n that is not a sum of 2 primes. So if I have a way of checking whether a program halts, I'll be able to refute the Goldbach conjecture, for example. Okay, so I really want to know. This is something, I really care about. Okay, so, so halting problem is important, of course, program verification, but also if you want to prove theorems automatically, you can do things like this with other conjecture, not only with this one. Yeah, please. Sahara?
I just had a question about this. And so as far as I understand, please correct me if I'm wrong, this thing runs from n2 to infinity. So this loop is gonna like try each n from 2 to infinity. And like, even if it like halts at some point, are we like ever
No,
gonna
no,
know?
if it halts, it breaks. I don't know. Now you see my programming skills. Sorry, I meant that if it doesn't find a counterexample, it will just go forever. But it will, it will halt, or it will print the answer at some point if it finds it. Okay, I meant that the loop will be. Maybe I need a while loop, right? While you didn't find.
I just meant like if it halts at a like n, which is very close to like somewhere in infinity, like it's gonna take like forever.
Oh yeah, it may take a very long time. There's no forever, right? If it halts in finite time. That's the magic. There's only now. It might be, I don't know, billiard or whatever are the numbers are. It can maybe very large, but it will be finite time. So yeah, maybe it's not realistic. Maybe you're telling me, okay, you can't like really refute the Goldbach conjecture because it will take too much time. Yeah, we'll talk about time next time. Okay. So yeah, admittedly, even if you can solve the halting problem, it will not solve all my problems in mathematics because it may take too long. That's a very valid point, and I'll touch upon this next time. You totally caught me on this one. Yeah, please, Jack.
Hey, yeah. Just to verify, you mean finite as in polynomial time, right?
No, I mean finite is finite. So for this talk, I won't talk about running time. I'll just talk about finite. Well, something either halts or it's looping forever. Okay, either there's some number and this will break, or it will loop forever, right? So those are the two options. And if it breaks, then it might be right. It might be a huge number. For this talk, I'm not talking about this. Okay, I'll talk about efficiency next time. But you're both right that if I really want to convert this to a theorem prover, I kind of have to talk about the running time too, if I want something to happen in my lifetime. Okay, yeah.
Okay.
So that's a valid point. Anyone else? Okay. Good. So this is okay. All I wanted to convince you is that this, at least I want it to be decidable, right? Maybe I also want it to be efficient, right? Let me dream, but let's first see if it's decidable. But how can I show that something is? How do I show that something is decidable? I give an algorithm, right? This is the algorithm for doing halting. How do I show that something is undecidable? Okay, I had this counting argument before, but how do I show that something specific is undecidable? Okay, so this is the next slide. Unfortunately, you probably saw it coming, halting is undecidable. So not only there are no efficient algorithm to check if a program halts on a specific input, there's no algorithm at all. And forget about polynomial time, I wish. Not even exponential time, not even triple exponential time, nothing. So halting is undecidable. There's no finite program that will halt and will tell me if P halts on X. So, okay, so it's, again, this is the, what I'm claiming is that halting problem is undecidable, meaning that there's no problem A, there's no Java program H, that if I fit to it a program P, the code of a program P, and an input X, then it will output 1 if P halts on X and 0 if it doesn't halt on X. And I only need this to happen in finite time. H needs to tell me in finite time if P halts on X. It's kind of confusing because there are two Java programs, but this is the Java program I'm trying. What is happening to my cursor? This is a Java program I'm trying to construct, and those will be the inputs. And I want to know if P will halt on X. This should be the output of H. Okay, so so this is a very famous theorem, by Alan Turing. This guy, this handsome guy, is Alan Turing. And this striking result has a pretty short proof. Let me show you the proof. Again, it's mind-blowing if you haven't seen this. Okay, so let's assume that there is a Java program, H, that computes halting, that does what I say here. Okay, so let's assume this. Now let's kind of enumerate all other Java programs. I told you, Java programs are just, I will look at them as like a long string, and I will order them in like an alphabetic order, like in the dictionary. A is before B. Okay, you have special symbols, but just order this. Okay, so I can have an order. It's an infinite order, but there's an order. First one, second one, so on. Okay. Now I will write a new program. I call my new program P star. So I have H, and I will construct a new program P star, and P star will be very sneaky. P star will be different than any of the programs in my enumeration. So on input I, it will be different than PI. So P star for input 1 will be different than the program P1 for input 1. P star for input 2 is going to be different than P2 on input 2, and so on. So it's going to be different than all of them. Here is my program. It's a very simple program. Again, my Java skills are not great, so this is pseudocode, but easy to convert. What is P star of I? What is my program doing with the input I? It will run H on PI and I. So it will check if PI halts on I, okay, using this H that I assume. So it will check if PI halts on I. If it does halt, then it's going to compute what is PI on I, and it's going to give the opposite answer. So if PI, when I run it on I, says 0, I'll give 1. If it says 1, I'll give 0, just for spite. And if it doesn't halt at all, if PI doesn't halt at all, I'll put something, let's say a 0. I don't care. Okay. So you see, for every I do something different than PI. I'm different than PI on the input I. If it halts, I don't. If it doesn't halt, I halt. And if it gives a 0, I give a 1, and vice versa. Okay, so that's great. A nice program. And as I said, P star is different than all the PIs. This is by construction. There is an input for which it's going to be different than any PI. The input is I. So it's different than all the programs. It's different than P1 on 1, then P2 on 2. It's just different than all of them. Great. So, but wait, I just assumed that P1, P2 are all the programs. I enumerated all the programs. P star is a program. What do you mean it's not in the enumeration? This is all programs. You're a program. You're supposed to be in the enumeration. So this goes to show you that P star cannot exist. It's not in the enumeration. It does not exist. If it's different than all programs, then it does not exist. Okay, but what do you mean? It does not exist, right? I show you the program. This is the blue stuff is the program. I wrote it down. Okay, so the only resolution to this issue is to say that H cannot exist. So yeah, I do have the blue stuff that can be converted to Java, blah, blah. The only thing is I assume that H exists. I assume they can tell if something halts. So this must be the bug. I cannot check if something halts. If I can check if something halts, then there is this P star, but it cannot exist. So P star does not exist because H cannot exist. And I got a contradiction to the existence of H. So there's no program that will tell me if another program halts. This is it. This is the entire proof of this theorem. Again, it's a beautiful proof. It's very sneaky. It's self-referencing, but it works. Questions about this in the chat, maybe? Oh, okay. Okay. Yeah.
Can you clarify maybe why P star isn't defined in a contradictory way, in the sense of like, okay, say, right, we enumerate all the programs, say P star is P10. So then you run P sub 10 of 10.
What I'm saying, P star cannot be P10 because P star I know is different than P10 on the input 10, right? This is how, what is P star doing if I is 10, right? It's checking if P10 halts on 10. If it does halt, it gives the opposite answer. So it cannot be the same as P10 because it gives a different answer than P10. And if P10 doesn't halt, then it halts. So again, it's different than P10. So what I know is P star is different than P10. Why? Because on the input 10, it's different than P10. So it can be the same program. And this is true for every 10, right? So it's different than all of them simultaneously. Again, it takes some, if you haven't seen this before, it needs to sink in. It seems like a trick, but it's a trick, but it works. It's simultaneously different than all other programs. So I showed you that for a specific input, what I constructed is different than each of the programs. So it's different than all of them simultaneously, but you can't be different than all simultaneously, because if you're a program, you need to be in the enumeration. You're not, you do not exist. H does not exist. Okay. Well, we'll see those kind of self-referencing things again. Disturbing, but works. Okay. So unfortunately, we have to deal with reality. Not everything is even computable. And again, I'm not talking about efficiency. It's not even computable. Okay, so halting is not computable. Is there anything else? Of course, there are many things. Most functions are not computable, but any other thing that we care about? Unfortunately, yes, many things we care about are undecidable. So I told you about something from computer programming, right? The halting program. Here's something for mathematics, equation solving. You want to solve equations. So here is a specific equation solving problem. This is called Hilbert-Tann's problem. We'll see this Hilbert dude soon, but he has many interesting problems. This is one of them. He will give you a multivariate polynomial with integer coefficients. Don't worry about this. Basically, things that look like this. You have many variables, right? X, Y, Z, and your coefficients are integers. And you want to just solve this equation. You want to know, but you want to solve it with integer values. So you want an assignment of X, Y, and Z, to all the variables that with integer points, right? That will solve it. Want to solve it with integer points, with integer assignment. Can you do this? You can't. There's no algorithm. Again, it's not about running time. It's about you just can't. You can try. Let's try 1, 1, 1, 1. Let's try 1, 1, 1, 1, 2, and so on. We will never be done with it. There's no way. So this is something we want, but it's just undecidable. Here's another thing that is undecidable.
Would it be decidable if we lifted the integer restriction?
Yeah. Then you can. There'll be other issues with the precisions and other things.
Yeah.
It will be decidable, for example, then you know that you kind of know that you can't use numbers that are too big, and you can just try them all. So some versions of this are decidable, but this is undecidable. Yeah. Good. So here is another example from biology now. And again, those are all over sciences and beyond sciences. Let's say someone gives me the rule of an epidemic. Now it's very timely. Okay, do not freak out. And I want to know if the epidemic will spread or die, or maybe this is about, organism living or dying. Okay, let me show you a concrete example. This is called Conway Game of Life. If you have OCD, this might be a problem. It keeps moving. This is the specific rule of, let's say, an epidemic, or maybe a form of life that is trying to spread. So if you're okay, so you see the animation I have here. Black cell is alive, cells are dead, and I have a great this grid of cells. So if you're alive, if you're black, 2 or 3 of your neighbors, you have 8 neighbors. If 2 or 3 of them are alive, you'll be alive in the next iteration. So it goes in iterations. And so it's something like, if you only have 1 or 0 live neighbors, then, you die of loneliness. If you have more than 4 or more, then, it's overpopulated. So this is kind of the sweet spot. And also, if you're dead, if you're white, but you have 3 living neighbors, you'll come alive. Okay, it's some rule of spreading. It doesn't, a specific rule. And the game is like, I give you the first, the board iteration 1. I just tell you which cells are black, like which cells are alive. And you need to tell me if life will continue forever. If for any iteration n, there'll be at least 1 black cell. Step forever, yes or no? It's a, it's a Boolean question, yes or no? Would life die out at some point? Would be all white? If it's all white, it cannot come back to life. Would it be all white or no? As you can imagine, undecidable. So thanks, but I don't know if you care about this specific rule, but you can think of other rules, and some other rules will be undecidable too. So things that make sense, things we want to solve, are sometimes undecidable. This is the hard reality. And I want to give you another, I think, cool example. But for this, I'll have to take a small detour, and I want to tell you about Berry's paradox. So here is Berry's paradox. Let me define x. X is like an integer. How do I define it? I said that it's the smallest number that cannot be defined in less than 15 English words. The definition of x. This is x for me. Okay, cool. But you see, this is, if I counted correctly, 14 words. Okay, the blue thing is 14 words. So the blue thing is a definition of x in less than 15 English words. What do you mean, right? So x is not the smallest number. It cannot be defined less than 15 English words because I defined it with 14 English words. So, again, like what? And again, her resolution. What's wrong with this argument? What's wrong is that cannot be defined in less than 15 English words is not well defined. It's not really a definition. It's a self-referencing definition. And actually, the only word that is not well defined is the word defined. What does it mean to be defined? Can you be defined by a circular definition? Okay, so again, this circular thing, the self-referencing thing, it messes up with your minds, but sometimes poses real problems. Yeah, please.
Is this somehow related to common graph complexity? Like this.
So you're trying to steal my thunder, I understand. Can I abandon you from this talk? Totally, you're totally on to me. Yeah. Okay, so let's go to what is not a surprise anymore. Thank you. Why am I telling you these things? Again, those are kind of mind puzzles that are disturbing, and we'll say that it can actually cause problems in math. We'll see it in a few slides. Okay, but Kolmogorov of complexity. Okay, so why did I tell you about Berry's paradox? Because it's very related to a thing called Kolmogorov of complexity. What is Kolmogorov of complexity? I give you a natural number n, and you need to tell me what is the Kolmogorov complexity of n. Actually, it's like, for me, I like strings better, but it doesn't matter. What is the Kolmogorov complexity of x? It's the length of the shortest Java program that output x and halves. Okay, I mean, this is a definition, right? Java is well defined, the shortest program. Okay. So at least it's well defined. Oh, this is what I'm saying next. Okay. So the Kolmogorov complexity of X is kind of the number of characters that you need to define X in some way, right? Using Java. It's like the smallest number of characters that you need to define this X. So now I define what was not defined. I define what is to define, and it's not self-referencing. Okay, and let me show you a cool thing about Kolmogorov complexity. I kind of claim that it measures the randomness in a number or a string. Just think of the digits of the number as a string. It's just easier to think about this. I'm saying that it kind of measures the randomness of the string of this number. So here's an example. Here's a string. We can kind of agree that it's not a random string, you know. Here's another string that was taken from one of those random generating things. It looks more random. And I want to claim that, you know, what is random? We'll talk about it also next time. Yeah, I talked about it. It's a central question, but we can agree that this does not look random. The first one does not look random. The second one looks more random. Why is that? One explanation is that the Kolmogorov complexity of the first one is higher than the second one, or one way to capture this phenomena is the first one has a Kolmogorov complexity that is lower than the other one. Here is a Java program for the first string that prints the first string. Okay, it's not 100. I was too lazy to count, but from 1 to number of repetitions, print 1, 0. Okay, it's a short string. It's a short program. What is the Java program for the second one? Well, I don't know actually, but this is safe, and I don't think we can do much better. Just print this crazy thing. So Java program needs to have this embedded in it. I don't know how to compress it, right? So this idea of Kolmogorov complexity is about compressibility. Random strings cannot be compressed. This is what Kolmogorov is kind of telling us. Maybe I can find some, maybe I can, instead of like, there's like 5 zeros, I can write 5 zeros, but I really don't know how to compress this. And I know how to compress this. And if the Java program is short, it means that I understood some logic, some rule I was able to compress. And if the Java program is long, I was not able to compress, so maybe it's random. And this is one of the definition of randomness. There's many other ways to try to capture randomness. Again, Yael talked about pseudo-randomness. I'll talk about randomness next time. They're different. There are other measures like information, like entropy, and so on. So there are other measures of randomness, but this is one measure that talks about the compressibility of the string. Okay, so Kolmogorov complexity is cool. Unfortunately, like many other cool things, it's undecidable. So here I just think of, I want to know if the Kolmogorov complexity of the string of the number is more than something or less than something. So it will be a Boolean function. I'm saying it's undecidable. And the proof for this, I won't give you the proof because I want you to do it in the homework if you haven't. And you'll see that it's kind of exactly Berry's paradox. So the observation was correct. This is how you show that Kolmogorov complexity is undecidable. You'll do it in the homework. But I think it's a very cool proof. So, okay, we can't tell if something is random, right? We don't know what is the Kolmogorov complexity. Maybe not the most useful definition of randomness practically. Okay, so the questions about what I was talking, I was trying to tell you a little bit about computability. I want to switch gears and talk about mathematical logic. And before, kind of the object we talked about was computation, Java program, how to compute, and now the object is proofs. How do we do math? How do we do proofs? And what is the connection between proofs and computation? I'll argue that they're very similar. We already saw this with this Goldbach conjecture, but I'll show you more of this here. So no questions, let me go into, oh yeah. Okay, so this is, if you remember this guy, this is this, I haven't shown you the picture before. Okay, so this is this Hilbert guy I was talking about with the 10, many problems. He's like a famous mathematician that was a German mathematician, very influential, that was lived about us, that was active about a century ago. And let me tell you why I'm telling you about him. So again, I'm talking about proofs in this section, and mathematical proofs were done for millennia, right? We have the Greek were doing this, and Euclid was doing it before Kant, and so on. So this was done in different level of rigor. So some proofs were done more rigorously than others. But in the 19th century, people were starting to notice, mathematicians were starting to notice disturbing signs about proofs. They're starting to notice that they can derive paradox or contradictions of various kind of ways. And this was disturbing. Let me show you one such paradox to explain what I mean, that, kind of the foundation of mathematics, of what it means to have a proof, were very shaky. So here's an example of like a shaky thing that you can do. This is called Russell's paradox. It's a very famous paradox in set theory. And Russell said, okay, let me construct the set R. What is the set R? Is the set of all sets that do not contain themselves as elements. So it's a set of all x's, such that x is not an element of x. Again, it's self-referencing and it's disturbing. It will all be like this, but we have to deal with this. It's a real problem, okay? X, so I'm taking all the sets that are not a member of themselves. So I didn't know if to call this X or S, right? Because they're elements and sets at the same time. Why is this disturbing? Cool, maybe we can agree that, this definition looks normal. However, it has a huge problem. So there are two options, right? Either R is in R. R is a set, right? So either R is in the set R or it's not. If R is in the set R, what does it mean? It means that it's a set that contains itself, right? Because R is in R. But then if it's a set that contains itself, it should not be in R, because R is a set of sets that do not contain themselves. So if R is in R, then R should not be in R. I have no idea what's happening with my cursor, but okay. If R is in R, then R should not be in R, and vice versa. So is it R in R or not in R? What's going on? So see, there is a contradiction here. There's a paradox here. And people constructed those kind of things. This is disturbing. Is math, all we were doing is wrong. There are contradictions. You can derive contradictions. You're in R and not in R. What's going on? So, mathematics as a whole was facing a crisis, a fundamental crisis of what's true and what's false, and how do you do proofs. Oh, I forgot to say this again. There are many paradoxes in this area. This is a very famous one called the liar paradox, and the liar paradox is the sentence: "This sentence is a lie." So if this sentence is, if this sentence is a lie, then it's not a lie, because it's not a lie, it's a lie. And if it's true, it's a lie. You see, it's the same thing. So I'm saying Russell paradox is basically this liar paradox. Anyway, back to the huge crisis and back to Hilbert. Hilbert was very disturbed by, Russell paradox and all the other paradox. And he decided that we mathematicians need to proactively find secure foundations for math. We should rigorously say what's a proof, how do you define a proof, how do now you get a problem set, you say all kind of stuff and it looks like a proof. Is this really a proof? What do you mean? And this idea of rigorous foundation for framework for mathematics was not new. Euclid before Kant was trying to do this, but what they came up with were not really rigorous stuff. In the 19th century, as I said, Russell, and there's a very famous book by Russell and Whitehead that was trying to lay those foundations. It's kind of notorious because I think around page 400, they're able to deduce that 1 + 1 is 2. So, okay, maybe not the easiest to work with. Anyway, people were trying to do this, and Hilbert said that, okay, this is the most important thing we can do right now, is just to work on those foundations. Otherwise, everything will be crashing down. And Hilbert had a two-phase plan. This is the first step. Come up with an axiomatic system, a formal language of well-defined rules that will allow you to prove any true statement. This is what he wanted. And this is what he thought, that if something is true, we should be able to prove it. So we need a formal system. I'll talk about what I mean axiomatic system and so on. But you want this thing that is very rigorous and that will allow you to prove everything that is true. And again, I'm not talking about how long would the proof be, then you can think about this, but I just wanted to be able to prove everything that is true, and of course not prove any contradictions. And he was looking for this, and he encourages other people to look for this. And the second part of the plan is once you have this framework, then find an algorithm for finding the proofs. Do it in an automatic way. And of course, back then he didn't really know what's an algorithm. It's not he didn't define an algorithm, didn't have this notion of a Turing machine or lambda calculus. This will come later. But he said that he wanted a mechanical process that halts in finite time, what we call an algorithm. So this is what he wanted, to have this framework, a rigorous framework, and to be able to automatically produce proofs. So you understand this, those slides are kind of sad. No one is happy. So this is not going to work out for him. But let me tell you more about what we mean a formal system, blah, blah. I think we say that, but sometimes we don't show it, what we mean. So what is a proof system, axiomatic proof system? What is he looking for? He's looking for set of axioms. Those are, I'll show you an example, okay? A set of axioms, which are formulas that we assume are true. This is the building blocks. We just assume that they're true. And rules of inference, deduction rules, which is kind of mechanical ways to derive theorems from axioms. So you need to have like the building blocks and how to infer things from the building blocks. So I'll give you examples. This is the most famous probably inference rule called Modus Ponent. Modus Ponent is, again, the most useful. Usually it's the only one you really need. And it says the following: if you already know that A implies B, and you already know that A is true, then you can deduce B. Okay, so if you know two things like A implies B, and you know A, you already proved those things, then you proved B. Makes sense. This is a derivation rule. This is an inference rule. So he was looking for a proof system. Again, I'll give you an example in a minute. And once you have the system, you can do proofs, like rigorous proofs. What is a proof? It's just a sequence of formulas. Well, again, I'll show you what it means. And every formula in the sequence is either one of the axioms. Axioms I just assume are true, or it follows for previous formula via inference, via, let's say, modus ponent. So maybe, the first sentence I have is A, the second sentence is A implies B, then the third one can be B, okay? And maybe A is true just because it's an axiom, and A implies B is true just because it's an axiom. I can deduce B, and I can build this way. So I think this is kind of our intuitive notion of a proof, right? If you do a geometry in high school, at least in my high school, we had to write it like this, say, from 1 and 5, I deduced it. Okay. Good. And the question is, what are those axioms? Where do they come from? What do they look like? And so on. Let me give you an example. This is called Peano arithmetic. It's a proof system that is supposed to capture number theory. That's a very good proof system. When you define a proof system, you define a vocabulary or a signature. It's kind of a set of constants you'll be using, set of functions and relations. For Peano arithmetic, we use the constant 0, just an object, just a drawing, right? It doesn't have an interpretation. Just, I will use this notation. And we use 3 functions: the successor function, the +1 function, the plus function. I mean, x plus 1 is successor, just the sum function, the product function. So those are the vocabulary. And now you can write your axioms using the vocabulary. Here is one axiom of Peano arithmetic. 0 has no successor. And formally, you will write something like this. When you write your axioms, you can use for all, exist, you can use imply, you can use equals. So there are some rules of what you can write, what sentences you can write as axioms. This is one axiom. 0 is not a successor. Okay, there's nothing smaller than 0. X plus 1 cannot be equal to 0. Okay, it makes sense. If you want to do number theory, you should be able to prove this. But I'm saying I'm taking it as an axiom with no proof. I will build on this. There's another thing. Successor function is 1 to 1. So if x plus 1 is equals to y plus 1, you can deduce that x is equals to y. Again, I'll take it as granted. This is my building block. For some reason, I decided this will be a building block. Of course, I want it to be true, right? It's like, I think it's true. And there are a bunch of other things that are, you know, you look at them and they all make sense, right? The sum is associative and 0 times anything is a 0 and so on. They all make sense, but why are those the building blocks? It's unclear, right? I can take any other sentences about the natural numbers. Why those? It's magic. They came up with this. I wanted to focus on maybe this one. This is the induction axiom. The induction axiom says that if something f is, let's say that f is something. Okay, it's a formula. It's a something. If something is true for 0, and for every x, if the something is true for x, it's true for x plus 1, you're allowed to deduce that it's true for every x. What do you mean? We've been doing induction all along. Nobody thought it was an axiom, I think. Like, I was like, what? I would just do this, right? It's natural. No, it's an axiom. You can do this because it's an axiom. Anyway, again, this is a set of axioms for piano arithmetic. Why those? I don't know. Like, obviously, they're all true, right? They capture my intuition. But why those and not others? I don't know, but the rules of the game is you want something concise that will be very expressive. Now, using this and modus ponens, this thing is A and A implies B gives you B. Using those things and, you know, the derivation rule, you should be able to prove everything or many things. And very surprisingly, almost all true statements about arithmetics we were able to deduce with this axiomatic system, with those few axioms and with modus ponens. And, you know, we've been trying this for over a century and we were able to prove almost everything from this. It's kind of amazing. It's like, okay, so nice. So maybe we can prove everything from piano arithmetic. Actually, the kind of standard axiomatic system for mathematics is called Zermelo-Franco. It's an axiomatic system for set theory, but can be used for any other theory. But anyway, maybe we're done, right? Maybe this is it. We just write piano arithmetic or we write Zermelo-Franco and we get everything we wanted and Hilbert is happy and, you know. And I already told you, it's never like this in this presentation. Everyone is sad. And apparently Hilbert's program came crashing down. And the one who's in charge of this is Ghetto. So here's, you know, Hilbert with his hat and his program to just to find a proof system in the sense I told you about, this axiomatic axioms and derivation rules and and from this we prove everything. And he proved true statement. This is what he wanted, and you know, it took a while, but then Ghetto was saying no, there's no system that will do this. You cannot write an axiomatic system and use it to prove all true statements. I should put a star. You can do this if you have contradictions. So if your axiomatic system says 0 is not a successor and 0 is a successor, it has a contradiction. Oh, this is, yeah. If you can prove something and the negation of the something, maybe you have an axiom saying something and another axiom saying negation of the something, or maybe by derivation you can get something in negation. If you have contradictions, sure, you can do anything. We kind of know, right? If you have a contradiction, you'll prove anything. But if you don't have a contradiction, there'll be true statements that you won't be able to prove. And this is extremely sad, right? We can't hope to do what Hilbert was trying to do. Oh, by the way, this is Ghetto was apparently doing it when he was like in his early 20s, and he was he was a PhD student. So if you guys consider grad school, this is kind of a medium to good thesis, I would say. Expect to get something like this. Anyway. Okay, so this is Ghetto, and again I can ask, oh, maybe I don't care about this. You know, we've done piano arithmetics, we were able to derive the stuff we wanted, maybe we're good. No, we're not good. Some very important statements that we care about are independent of our axioms, meaning they cannot be proven. One of those things is called the Continuum Hypothesis. Again, I think I wrote something in the homework about this. The continuum hypothesis says that there's no cardinality between countable sets, like natural numbers, and the real numbers. There's nothing in between. There's no cardinality in between. And I give you the definition. And this took a very long time. It's a very celebrated result of Paul Cohen in the 60s. There's a funny story about him going to MIT, an MIT logician, and is asking, what is the biggest open problem you have? And he was saying, can you prove the continuum hypothesis? And then it took a few years and he was showing that it's independent of the axioms. So anyway, this is a specific thing you want to do if there's a cardinality between natural numbers and reals, and it just, you can't prove it. It's not like you cannot prove it. It does not depend on our axioms. It's independent of our axioms. Maybe a more disturbing thing is you want to prove, I told you, maybe you have a contradiction. Maybe you can derive T and not T. Maybe you can derive contradiction. That's worse than anything else. Let's say there are some things you can't prove. Continuum hypothesis. Okay, a bummer, but you can live. What if we have a contradiction, like a real contradiction, like in the set theory I told you about? There was a contradiction, right? There's something wrong. What if there's something wrong and we don't know about this? Unfortunately, you don't know if there's something wrong. You can't tell if there are contradictions. This is an even more disturbing theorem by Ghetto. This is Ghetto's second theorem that says, if you were able to show that you're consistent, that you don't have contradictions in your axiomatic system, it has a contradiction. So from contradiction, you can deduce anything you want. But if there are no contradictions, you will not be able to do this within the system. Anyway, again, disturbing stuff, and making this story shorter. Hilbert wanted to get this amazing axiomatic system that will prove everything. Ghetto was showing that there's just no way. This is just not correct. It's impossible. And let me just throw Alan Turing in the mix. This is Alan Turing kind of killed like the second step. There's nothing automated. Even things you can prove, you cannot prove in an automated way. So, dream is gone. But what I want to do is quickly give you a proof, like a very high level proof for Ghetto's theorem. So again, I'm trying to show that there are theorems that cannot be proven, like true things that cannot be proven. Okay, so this is about his original proof. I'll show you a different proof, but his original proof was kind of is a tweak on the liar paradox. So if you remember the liar paradox, it's kind of saying this sentence is a lie. And if it's a lie, it's a truth. And if it's a truth, it's a lie, and self-referencing. Ghetto changes this to say this sentence is not provable. And if you can prove this sentence and it is provable, you see the same kind of phenomena. So he was writing this sentence and was arguing about this. And I know I make it sound easy, you write a sentence, but okay, so first self-references is the key for this and for everything we've done. But the real problem is like writing this in your axiomatic system. The formalism is not a mere formalism. It's the main thing here. And he was able to nail this. He was able to rigorously write this sentence and reason about this in his axiomatic system and so on. So this is the original proof. I want to show you another very popular proof using the halting problem and kind of tie those ideas of proof and computation. Again, this is a proof using halting. I'll show you that if you assume that every mathematical statement, every true theorem can be proved, I'll show you that I can find a Java program for the halting problem, which I know is wrong, which I know does not exist. I showed this before. Okay, so let's, and then this will show that there are some theorems that cannot have a proof. Okay, let's assume for contradiction that every true statement can be proved. Okay, I will derive a contradiction. Let me show you how, using this assumption, I will construct a program H for halting. Okay, so program H takes, again, Java program P and an input X and answers whether P halts on X. And this is what the program will do, to go over all possible proofs, and we'll find the first proof that shows that P halts on X or that P doesn't halt on X. And by assumption, one of them should exist. Okay, so you see here's my Java program. So again, this is the Java program and it needs to tell me in finite time if P halts on X. And this is what I'm doing. I'm going over all Y's. Y's are, I think of Y as numbers or strings. It's the same. I can convert string to numbers. So if you want to think about a proof as a string and convert it to a number. So let's say I go over all possible proofs. Okay. Now I check if Y encodes a proof that P halts on X. Is Y a proof for this? Hopefully I can check proofs, right? I have this axiomatic system and it should be easy. I'm just checking that my tense, my sentence 10 is really deducible from 7 and 5, for example. Should be an easy process, automated process, right? Once I have my axioms, I can check. So anyway, I go over possible proofs and I check, is this a proof that P halts on X? If so, I say yes and halt. I mean, this is halting, okay? It's again the same thing. I break out of the loop. And I also check if it's a proof that P doesn't halt on X. And if it's a proof that it doesn't halt on X, I halt. I say no and halt. And I kind of assume like P should halt or not halt on X. There's reality. A program halts or does not halt. There is a truth. I just don't know what is the truth. But if I assume that every true thing can be proved, then there should be a proof for either P halts or for P doesn't halt. Eventually, I will find some proof. So eventually, I will find a Y that proves this, or I will find a Y that proves this. It may be long time. Y may be a very long proof, but eventually I should find one like this. Okay, so I just solved halting. What's the catch again? I know I cannot solve halting. I cannot have a program that computes halting. The catch again is that for some theorems, for some Turing machines, there will not, for some Java programs, there will not be a proof that they halt or a proof that they don't halt. Okay, some P's are like this. So it cannot happen that for all P's, either I find a proof that they halt or a proof that they don't halt. So this is not really a machine for H. I mean, my assumption that that I have proofs is wrong. This is the only explanation because I know I cannot have a Java program for the halting problem. Okay, and this is it. This is how you show Ghetto theorem. Again, it's not easy to do it totally formally. It takes some effort, even in this case. But this is like the overall idea. And you can see how computation and how proof are kind of very tied together in this sense. Yeah, I think this is all I have. This is all I have.